Hello, my name is Corey Beasley. I am in Math 2000 and I attend Challenge 2016. And today I'm going to go ahead and do the homework for Math 2000. This is part 2 of the homework, or the second video assignment, and I'm going to show you how to work with integrals a little bit, or explain how to work with them at least. So, the basic rule of integration, or the one that I like to refer to usually when I'm integrating anything, is what you're going to do is if you have a function, and I'm going to take a very simple function, the function of x. I'm just laying down the basics, and I'm going to try to go through quickly because the actual problem involves a little bit beyond the basics. So you have a function, f of x, and the function is going to be really simple, x itself. In order to integrate any function, essentially, or any term of a function, what you're going to do is increase the power by 1 and then divide by that new power. So if you had x by itself, you'd increase the power by 1, so it'd be x squared, and then divide by that increased power, x squared over 2. That's how you integrate a function. Now, I'm going to throw another one up really quick. So if you have because I forgot to explain one thing. If you have an integration, and say if you have x squared, you do the same thing that I just did, increase the power by 1, so it's now going to be x cubed, and then divide by the new power, x cubed divided by 3. But I forgot to speak of this step. You're going to also add a constant to each integration, if it's indefinite. Now the reason you add a constant is because you don't know what the value could have been before you had integrated the function. So say if you were to derive something, once you derive, say, a number by itself, if you have 24, and you were to derive this, you get 0. However, if you integrate 0, you're going to get x. Or you're not going to get anything. So you have to add a constant to understand, or to make up for the value that you would have made 0 initially. Now, we're going to talk about integrating with boundaries, or definite integration. Now, definite integration is basically the same as regular integration, or indefinite integration, except the difference is you're restricted between two boundaries, which are usually vertical lines or x equals. So if we have, say, x equals a and x equals b, and then we have a coordinate graph right here, I'm going to go ahead and draw a and b, and we're trying to integrate, we'll say x squared, a quadratic equation, and we have it like this. As we know, when we integrate, we're finding the area below the curve. But when you have definite integration, you're trying to find the area below the curve that's in between the two given points on the horizontal axis. So we're actually going to take away this part right here. We're only going to integrate from a to b. Or actually from b to a, because b is at the top. So we're going to be going backwards, which just means that the value under the curve is going to be negative. So now we can actually get to the problems that we were given. The very first integration problem was actually, we were given r by itself to the dr. We were told to integrate that from the bounds of 5 square root of 2 to the square root of 2. Now, as we solve out this integration, I'm going to also show you how to actually incorporate the boundaries into an integration. And it's really simple. So what we're first going to do is we're going to go ahead and integrate r by itself. So r is going to become r squared divided by 2, as I showed you earlier. And now that we've gotten rid of the integration sign, we still have these boundaries to adhere by, but we don't need this integral anymore. So we have r squared divided by 2, and then we're going to evaluate this problem from 5 square root of 2 to the square root of 2. Now, as you evaluate something, that's just basically saying that you're going to be finding the integration between the two curves. Between the two vertical points on the curve. Now, if you ever see this evaluation symbol right here, and you have 2 points to evaluate by, the way that you're going to actually properly do this is you're going to plug in the top point to the equation and solve that out, and then subtract the bottom point plugged into the equation, and you're going to solve that out. So I'm going to go ahead and do so right here at the bottom. So we have 5, the square root of 2. That's going to be squared divided by 2. That's the top boundary. Minus the square root of 2 by itself. Squared divided by 2. That's the bottom boundary. As you can see right, we have the bottom boundary, sorry. And we have the top boundary. So that's how that's done. now that we have all numbers, we can go ahead and just algebraically solve this out. And we can get the solution for the integral of r from 5 to the square root of 2 to the square root of 2. So if we go ahead and solve this out, do a little bit of algebra right here, as I said before. We have 5 to the square root of 2 squared, which is going to be 25 times 2, which is 50, divided by 2, which is just 25. So I'm going to go ahead and put 25 right here. And then we're going to subtract 2, the square root of 2 squared, which is just going to become 2 itself. And then 2 divided by 2 is 1. So 25 minus 1 is going to basically be our answer to this. And that's going to give us 24. And 24 is the area under the curve of r from the square root of 2 to 5 times the square root of 2. Now, as I said before, if you have a definite integral, otherwise an integral that's bounded by vertical lines, you don't need a plus c. So 24 is going to be your answer. That's the first problem. Now moving on to the second problem. We are told to find the integral of this function, and the function is 2x divided by 1 plus x squared dx. And then we're evaluating this from -1 to 1. Now the evaluation at this point in time is a little bit more simple because we don't have any square roots. It's just a simple -1 and a +1. The tricky part for this problem is going to be the actual integration itself. You're going to see that we have a fraction, and there's a different process for every fraction, whether you're integrating or deriving. When you're deriving, you have to use the quotient rule. However, when you're integrating, you're going to use a thing called u substitution. And I'm not going to entirely address u substitution, but I'm going to walk through the process. So basically what we're going to do is we're going to find a value and substitute it for u. Usually that value is the greater degree of the x, so the x to the greatest degree. Right here, the x to the greatest degree is x squared. So we're going to take x squared and make it equal to u. Now the trick with substitution is, u substitution is, after you do this, you're going to go ahead and derive both sides of the equation. So you're going to get a du, and then this derived is just 2x, and then dx is the result of deriving. Now, you'll notice in the name, I'm sorry, actually, let me backtrack for a second. The u substitution is actually x squared plus 1. Is that understandable? Because we have the x squared plus 1. We're going to just substitute the bigger value basically for u. Now, hence the name substitution. The biggest part of a u substitution is once you actually assess the u and the du value, you're going to now substitute that back into the integral. So we have, and you're trying to make that perfect substitution. So we have x squared plus 1, x squared plus 1. So you can go at the bottom easily and cleanly. And then we have 2x dx, 2x dx. So du can go at the top, and we'll just put it right there. And that makes everything nice and clean. And we still have from 1 to -1, or -1 to 1. So once we've done this substitution, we go ahead and we solve the integral as we would normally. The integral of 1 over anything is going to become the natural logarithm of that value right there. So we try to solve this integral, and we get the natural logarithm of u plus c, the du becomes plus c. But we don't need this plus c, however, because we have a definite integration. So we're going to take that out. And we're going to still evaluate from -1 to 1. Now the last step of the u substitution is you're going to go ahead and resubstitute that u that you had earlier in for what you just had in the integrated function. So I'm going to write it down here. You're going to have the natural log of 1 plus x squared. Evaluate it from 1 to -1. Now that we've done like I said, the most complex part of the problem is going to be the actual integration itself. Now that we've done that, we can move ahead to assessing the bounds of the integral. So I'm going to go ahead and plug this down here. We have the natural log of, we're going to plug in 1. So 1 plugged in x squared is just going to become 1. So the natural log of 2 minus, and then 1 plugged into that is also 1. And -1 squared is going to become 1. So the natural log of 2 minus natural log of 2 is going to be equal to the answer. And as we know from basic algebra, something minus itself is going to be equal to 0. So we get 0 right here. And that's actually going to be the final answer. So you try to evaluate this, the integration of 2x divided by 1 plus x squared from negative 1 to 1, and you're going to get 0 as your answer. And just a side note, I know from time to time as I addressed the bounds of the integral, I might have said 1 first and then said negative 1 second, but you're always going to be addressing it from negative 1 to 1. You're going to be going from the bottom to the top. So just to run through it really fast again, if you have A and B, and you have a coordinate plane, you're basically integrating from B to A. Those are the bounds. And then you take the function f of x, and then whatever the function is, you're just going to integrate from that area. And that's going to be how you solve the problem. Again, thank you. My name is Corey Beasley, and have a great day.